I'm Anil Kumar. In this particular video, I'm going to discuss fundamentals about trigonometric identities. We have 8 examples. With the help of these 8 examples, I'll show you different strategies which we can apply and what we really need to know so that we could prove any identity. Well, that's the motive of this particular video. So let me talk about Pythagorean and reciprocal identities. Pythagorean identities are sine square x plus cos square x equals to 1, 1 plus tan square x equals to secant square x, and 1 plus cot square x is cosecant square x. Right? These are Pythagorean identities. Reciprocal identities are you could write secant x as 1 over cos x, cosecant x as 1 over sin x, and cotangent x as 1 over tan x. Is it okay? Another important formula which you need to know is to write tan x in terms of sine and cosine. So tan x could be written as sin x over cos x. That should help you to prove most of the identities, right? So that's what we need. Pythagorean identities and reciprocal identities, as you can see here. Now these are different strategies. First strategy, let me number them. Then we'll talk about these strategies and then solve or prove identities. First one is express in sine and cosine. So for example here, we have cosecant. We can apply strategy number 1 here. Second one is apply Pythagorean identities, which are these, right? So since we have square terms, cos square, you could write this as 1 minus sine square x, something like this, correct? 1 minus cos square x is sine square x. So that means you could add second strategy. If you do these two, you will be able to prove this identity very easily. So what I'm trying to say here is there are strategies. Combination of these help. So we need combination of special strategies for proving identities. Let me say that, right? Now I hope it makes sense. So we're talking about 4 strategies here. Then we have to rationalize or factor. To factor, important formulas to remember are a plus b times a minus b is equals to a square minus b square. So if you are given difference of squares, they could be written as product of sum and difference. Very important to understand. And you should also remember the formula. What is a plus b whole square equals to? It is a square plus 2ab plus b square. And if you have a minus b whole square, then this term is negative. Perfect. So once you know these few things, you should be in a position to do 90% of trigonometric identities, right? Now let's go through these. The first one, I think we should apply strategy 1 and 2. The second one, we have tan. So this, we could say tan x equals to sin x over cos x, as I was saying. So strategy 1 is good enough here. Here we have secant minus tan x. Here I'll prefer to rationalize. We need some conjugate there, correct? So I prefer to rationalize or multiply by 1. You understand? Multiply by 1. So you could also do replace 1 by secant square x minus tan square. That will be a great strategy. And then apply factoring, difference of squares. So whenever you see 1, it could be replaced by Pythagorean identities, which I'll take up in the next video and elaborate. So here you could adopt strategy 1, which is expressing, or you could, I prefer to do strategy 4, right? Multiply both sides by sin x plus tan x, get your result. Here we are seeing 1 plus cos x, we want sin x. So in this case, multiply by, we'll apply strategy 4, divide both sides by cos x to get the result. Sin x, tan x terms, Strategy 1 is simple. Convert sine into secant and tan into sine and cosine. You will get your result. In this case, you could multiply by the conjugate. So rationalize could be a good strategy. Here, cosecant, so that means express in sine and cosine, strategy number 1. So combinations help, right? So you'll find once you apply 1, you get sine beta plus 1 times 1 minus sine beta. So you may have to apply 3 also. So combination of 1 and 3 will help you solve this. With that in mind, let's now move forward. I'll first explain you these two strategies and their applications, and then we'll move forward and simplify or prove all these strategies. And I hope you'll find this video very useful and interesting. It is very important to remember that whenever we are proving trigonometric identities, we always say that left side is equal to right side. So we always say left side is equals to right side. To prove any identity, you could start from left side or right side, correct? So this is the equation, equal to sign. That side is the left side, this is right side. Normally, you have to start from a side which is more complicated. So the criteria here is also start from complicated side. Also remember that every trigonometric identity has restrictions. So second thing to remember is restrictions. Now, we do not mention restrictions while proving. They are understood. For example, when I write tan x, I know cos x cannot be 0, right? So we will never write cos x is not equal to 0. Do you understand? It is understood. So it is implied. So in our proof and most of the books will not write restrictions while proving identities. Denominator cannot be 0 is implied. That's very important to understand. Okay, so all trigonometric identities, we need to prove left side equals to right side in their domain to be specific, correct? And the domain is never specified. It is that denominator cannot be equal to 0. With that in mind, let's move on and see how to prove trigonometric identities. Let me just take a point in a Cartesian plane, and from there we'll develop Pythagorean identities, which are fundamental identities to prove any trigonometric identity. So let's take a point P at a distance r, and let the coordinates of point be x and y. In that case, it really means that along the x-axis, the distance of point P is x. So if I draw a perpendicular, I get a right triangle. So this distance is x, horizontal distance, and the vertical distance is y. If the angle is theta here, in that case, we can write x square plus y square as equals to r square, right? Using Pythagorean theorem. Now if I divide each term by r square, then what do we get? We get x over r whole square plus y over r whole square equals to 1. Now what is x over r? It is cosine theta, right? So I hope you remember. Let me write down here. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tan is opposite over adjacent side, right? Now x over r is cosine of theta, so we get cos square theta plus y over r is sine square theta is equal to 1. Now this is a fundamental trigonometric identity which is very helpful to prove most of the identities, right? Now we could actually rearrange this and use it in different forms. We could write this as cos square theta equals to 1 minus sine square theta. We could also write sine square theta as 1 minus cos square theta, right? You could actually factor them also and write them as 1 plus sine theta times 1 minus sine theta. Similarly, 1 minus cos square theta could be written as 1 plus cos theta times 1 minus cos theta. Right? So all these are derived from the fundamental Pythagorean identity cos square theta plus sine square theta. Correct? Now, if I write sine and cosine in terms of secant, cosecant and tan, we can get other identities from here. To give you an example, if I again start with x square plus y square equals to r square, and instead of dividing by r square, if I divide by x square, then what happens? X over x is 1. Y over x is tan, right? So you get tan square theta equals to secant square theta. So that is the second Pythagorean identity which we can always use. And the third one you can get by dividing x square plus y square equals to r square by y square. What do you get this time? X over y is cotangent, right? So it is cot square theta plus y over y is 1, and r over y is reciprocal of sine, which is cosecant square theta, right? So that becomes the third Pythagorean identity. Is that correct? So these are the three Pythagorean identities which we are going to use many times. Well, as you can see from here, we could rewrite that. I could write now 1 as equal to secant square theta minus tan square theta. I can also write 1 as equal to cosecant square theta minus cot square theta. So 1 could be written in many different ways. Also, as we learn, cos square theta plus sine square theta. Is it okay? So these are different ways of writing 1 and relating sine, cosine, tan, secant, cosecant, right? Let's move on and see the second kind of identities, reciprocal identities. So reciprocal means 1 over, right? So 1 over sine theta is reciprocal of sine theta, which is written as cosecant theta. 1 over cos theta is secant theta, and 1 over tan theta is equals to cotangent theta, correct? You could actually many times write tan theta as equals to ratio of sine and cosine, sine theta and cos theta, or cotangent theta as cot theta. Let me rewrite. So cot theta as cos theta over sine theta, right? So if you write like this, you can write all trigonometric ratios in the form of sine and cosine. That really helps to prove trigonometric identities. Now, let me give you an example here, which can really help us to prove trigonometric identity very easily. Let's take an example of 1 minus cos square theta times cosecant square theta. We have to prove that this is equal to 1. Now, 1 minus cos square theta, we can apply the trigonometric identity which we just learned. That is sine square theta, correct? And cosecant square theta is, cosecant is reciprocal of sine, correct? So it could be written as 1 over sine square theta. So what we see here is that the left side is 1 minus cos square theta, which is sine square theta, times cosecant square theta, which is 1 over sine square theta, and that is indeed equal to 1, which is the right side. So the idea here is to start from left side and prove the right side. You can get identities proven. Now let's move on and apply different kinds of strategies. One of our strategies is to express in sine and cosine. So normally we can always write tan x as a ratio of sine and cosine, right? As sine x over cos x. This is very useful always to write as. But if I want to write tan only in sine or only in cosine, how can I do it? So let's take this exercise. So in this exercise, what we'll do is express tan x in sine x. So not as ratio of sine and cosine. If that is the case, what can you do? Well, we know that sine square x plus cos square x equals to 1. So that means we could write cos square x as 1 minus sine square x, or cos x as square root of 1 minus sine square x, correct? So whenever you do square root, you have to write plus or minus. Now depending on in which quadrant x is, we can actually figure out which sign to take, right? So we know all are positive here. Sine is positive in quadrant 2, tan in 3, and cosine in 4. So depending on that, we can select the sign. But that also gives you an idea that if I have to write tan x as only sine x, what can I do? Tan x is sine x over cos x. I could replace cos x by that function, right? So I could write this as sine x over square root of 1 minus sine square x plus and minus, correct? Now if I have to express tan x in cosine x, then what should I do? So you can actually pause the video, work it out, and then check with my solution. I could write tan x as ratio of sine and cosine, correct? I have to get all in cosine terms. That means sine could be written as square root of 1 minus cos square x plus and minus divided by cos x. You get an idea, right? So you could express any trigonometric ratio in terms of sine and cosine. Now let us discuss special strategies for proving identities. We have already used one strategy, and which was write all terms in sin x and cos x, right? That is the first strategy. Now we'll consider 3 more. So I'm writing this 2, 3, and 4. We're going to now apply Pythagorean identity, rationalize or factor, multiply both sides by expressions equal to 1. Right? So both sides could mean numerator and denominator, or could be left and right side. So as an example, I have 1 minus 2 sin x cos x divided by sin x minus cos x equal to sin x minus cos x. That's the identity we need to prove. Proving identity means we have to show that left side is equal to right side. That is what we have to show. Also remember, in identities we have restrictions, right? So remember that we always have restrictions. Restrictions are that denominator cannot be 0. Cannot be 0, right? Normally we don't specify it. It is kind of assumed that we are talking about the domain which is feasible for the given function. Is it okay? So these restrictions are always there. Identities are always true, except for at these restrictions when the denominator can be 0. Is it okay? Right. With this in mind, let's continue now. So here I will show you 2 different strategies, and then we'll actually see how we can apply different strategies to prove any identity. So here we have 1 minus 2 sin x cos x divided by sin x minus cos x. So what we can do here is we can apply Pythagorean identity, which is sin square x plus cos square x equal to 1. So I can replace this 1 with sin square x plus cos square x equals to 1. So if I do so, the left side could be written as, I'm replacing 1 with sine square x plus cos square x, and we have minus 2 sine x cos x. Do you see that? So I've started with the left side and I've replaced 1 with sine square x plus cos square x equals to 1. So that means I've applied the strategy number 2 here. In the denominator, we have sine x minus cos x. Now, the numerator is equal to sine x minus cos x whole square. And the denominator we have sine x minus cos x, correct? Now, I hope you remember how we get this. We know that a minus b whole square is what? Is a square minus 2ab plus b square, correct? So you can treat, in this particular case, let me use another ink, we can treat a as sine, right? So we have a square plus b square minus 2ab. Do you see that? So we could apply this formula and we wrote this as a minus b whole square. Is that clear? Once you write like this, you could simplify, cancelling square with the denominator. What do you get? You get this as equals to sine x minus cosine x, right? Which is equals to right side. So we have proven that left side is equals to right side, correct? So that, let me call this as our method number 1, right? So let's call this as our method number 1. And now in second method, we'll start with the right side, okay? So right side is given to us as sine x minus cos x. What do we need? We need sine x minus cos x in the denominator, okay? So if I multiply by 1, that is to say, I could multiply this by sine x minus cos x divided by sine x minus cos x. Now this is 1, correct? This is as good as 1. So multiplying by 1 does not really change anything, but it helps us to prove an identity. Let's see how. We could write the numerator now as sine x minus cos x whole square. And in the denominator, we have our term sine x minus cos x. Let us expand the numerator using this formula. We get sine square x minus 2 sine x cos x plus cos square x, right? Denominator is sine x minus cos x. In the numerator, we can combine the terms sine square x and cos square x. We get sine square x plus cos square x minus 2 sine x cos x divided by sine x minus cos x. Now what is sine square x plus cos square x? We know it is 1. So we get 1 minus 2 sine x cos x divided by sine x minus cos x, correct? So you could also start from the right side and then get to the left. But normally we'll recommend to start with the left side, which is more complicated. So always start with a complicated side, simplify. In this case, we kind of added the complication and get the result, which is kind of a difficult approach, right? Here's another interesting example where we are going to use special strategies to prove identities. The question here is to prove, we'll prove sine x minus 2 sine cube x divided by 2 cos cube x minus cos x equals to tan x. Now as you see, the left side is more complicated. So let's begin with the left side. Left side can be written as sine x, let's copy it first, 2 sine cube x over 2 cos cube x minus cos x. Now we are going to use this strategy to factor and then simplify. So we'll use this strategy, the second one this time. In the last example, we used first and third, correct? Now let's factor. So if you factor, what do you get? You can factor sine x from the numerator. You get 1 minus 2 sine square x. In the denominator, you could factor cos x and you get 2 cos square x minus 1. So you can see tan x is already there. These terms, if they cancel out, you have achieved what you wanted to achieve, right? Now, so at this stage, what you can do is you may write 1 as sine square x plus cos square x. You could do that, right? Now, since you see that, the denominator is in terms of cos square x, what you can also do is you can replace this 1, you could replace sine square x with 1 minus cos square x. You could do that also. You could also do this, sine square x equals to 1 minus cos square x. You could adopt any of these strategies to actually prove. If you replace 1, you have to replace both ones and get your result. If you replace the numerator, then 1 can work for you, correct? So let's use this particular form and only change the numerator. So we get sine x over cos x. We already have this. Here we'll write 1 minus 2 times, instead of sine square x, I'm writing 1 minus cos square x. Is it okay? So I'm only changing this part. So we get 2 cos square x minus 1 in the denominator. Now, we have sine x over cos x. And here when you open the bracket, you get 1 minus 2 plus 2 cos square x divided by 2 cos square x minus 1, correct? Now you can clearly see 2 cos square x, 1 minus 2 is minus 1. So this could be written as sine x over cosine x times 2 cos square x minus 1 over 2 cos square x minus 1, correct? Now they will cancel out, leaving with sine x over cos x, which is tan x, which is equals to right side. So that is how we can prove left side as equals to right side, correct? So in this particular case, we use the strategy to factor and also Pythagorean identity to prove our trigonometric identity. Okay, so now let's do the rest of the questions quickly. We have cos theta plus tan theta at sin theta equals to secant theta. Now what should you use? Well, we have to convert each term into sine and cosine. That should help. So we'll start with the left side, which looks more complicated. It is cos theta plus tan theta sine theta. So I'll just replace tan theta with ratio of sine and cosine, right? And then simplify. So if I take a common denominator, which is cosine theta, I get cos theta times cos theta as cos square theta. Here I have sin theta times sin theta, which is sin square theta, correct? And what is cos square theta plus sin square theta? Pythagorean trigonometric identity, we know cos square theta plus sin square theta is equal to 1. And therefore, we could write this as equal to 1 over and therefore we can write this as equal to 1 over cos theta, and 1 over cos theta is secant theta, which is the right side. So we have shown that left side is equal to right side, correct? Next question is, we need to prove 1 over secant x minus tan x equals to secant x plus tan x. Now name the strategy. What should we use to prove it? We'll again begin with the left side. You could begin with any. We have 1 over secant x minus tan x. Now what you could do is you could multiply both sides by secant x plus tan x, correct? Which is as good as multiplying by 1, correct? So when you do that, you get the required numerator, which is secant x plus tan x. However, in the denominator, what do you get? You get secant square x minus tan square x. Correct? Now, this factoring is very important to understand. A plus b times a minus b is equals to a square minus b square. So that is the strategy. Correct? Now here, we are looking for Pythagorean identity to relate tan and secant. What is that identity? Well, it is 1 plus tan square x is equals to secant square x. You can rearrange, write 1 as equals to secant square x minus tan square x. So the denominator is indeed 1. So we could write this as secant x plus tan x over 1, which is equals to secant x plus tan x, and that is the right side. Is it okay? So we have shown that left side is equals to right side. So here we multiplied by 1 to get our result. You could have done, you could have replaced them into sine and cosine, but that will be longer. The next here is cosecant square theta plus tan square theta minus cot square theta equals to secant square theta. What strategy should we use? If you look at these terms, do they remind you of something? Well, we know what is 1 plus cot square theta. It is cosecant square theta, right? So if you rearrange, you get 1 as equals to cosecant square theta minus cot square theta. Perfect. And you also know 1 plus tan square theta is secant square theta. So if you use two of these Pythagorean identities, it can be proven. Let's begin with the left side. Left side is cosecant square theta plus tan square theta minus cot square theta. Let's rearrange. We get cosecant square theta minus cot square theta plus tan square theta. So this is the left side. And as you know, cosecant square theta minus cot square theta is 1. So we get 1 plus tan square theta, and 1 plus tan square theta is secant square theta. So we get secant square theta, which is the right side, right? So we have shown again, left side is equals to right side. You should remember all these trigonometric identities are proven in their domain, right? So the denominator cannot be 0. Remember that. So in this case, sine and cosine cannot be 0. Now the example here is to prove 1 plus cos x divided by 1 minus cos x equals to secant x plus 1 divided by secant x minus 1. Now what strategy can you use here? Well, you could write secant x as 1 over cos x. So you could start with the left side and prove. You could start with the right side, changing secant as cosine, and then get to the left side. But in this case, we are going to show you another very important strategy, and that is, we'll divide both numerator and denominator by cos x, right? So we can say divide both numerator and denominator by cosine x. See what happens. Let me rewrite the question. So we have 1 plus cos x in the numerator. We are going to divide this by cos x, both the terms, and we have 1 minus cos x. We'll divide both them by cos x, right? Since we are dividing both by cos x, it means multiplying by 1. Is it okay? So that is the left side for us. So what do we get? We get, when you divide, we get 1 over cos x plus cos x over cos x over 1 over cos x minus cos x over cos x, correct? Now 1 over cos x is secant x. So you could write this as secant x plus 1. And here we have secant x minus 1, right? Which is the right side. So instead of taking common denominator and doing, we can actually divide and then do. So this is also a very interesting strategy. And of course, cos x will not be equal to 0. So that is a kind of restriction. We normally do not specify that, but it is understood when we are proving identities. Here's another example where you can again use the same strategy which we used in the previous example. I would like you to pause the video, answer this question, and then look into my suggestions. So the question here is, we need to prove secant x minus tan x divided by 1 minus sin x as secant x. Secant x, as you know, is 1 over cos x, correct? So that is the one. Or you could write them as sine and cosine. So strategy 1 could be, we could divide by cos x. Second strategy could be to write in sine and cosine. Now, since we need secant, we could divide by cos x. That's a good strategy. Anyway, let us see how to do it. So you could adopt any one of these. Let me this time use this strategy, which is write in sine and cosine. What is secant x? We'll start with the left side, which is secant is 1 over cos minus tan is sine x over cos x. And in the numerator, we have all this. In the denominator, we have 1 minus sin x. Now we can take cos x as a common denominator. So we get cos x, 1 minus sin x, and denominator is 1 minus sin x. Is it okay? So now, clearly, you could write this as equal to 1 minus sin x over cos x times 1 over 1 minus sin x, correct? 1 minus sin x, 1 minus sin x cancel. You get 1 over cos x, which is secant x. Is that clear? So this cancels. You could have cancelled here also. You could have cancelled here also. But this is another way of writing division as multiplication by 1 over the same term. And you can prove that left side is equals to the right side, correct? So it could be done in 3 steps. Here is another example. We have 1 minus cos x divided by sin x equals to sin x over 1 plus cos x. So let's begin from the right side this time. We have sin x in the right side over 1 plus cos x. Since I need 1 minus sin x, 1 minus cos x, let me multiply by 1, which is 1 minus cos x over 1 minus cos x. Do you see that? We're effectively multiplying by only 1. So we get sin x times 1 minus cos x in the numerator, and the denominator is 1 minus cos square x, since you know a plus b times a minus b is equals to a square minus b square. So this is a plus b times a minus b, which gives you a square, 1 square is 1, minus cos square x. Now we also know that sin square x plus cos square x is equals to 1. So 1 minus cos square x is indeed sin square x, correct? So we get sin x times 1 minus cos x. We are not disturbing it since we need 1 minus cos x. We didn't open this. Do you see that? And the denominator could be written as sin square x, 1 minus cos square x. Now one of these get cancelled. We are left with what? What we need, which is 1 minus cos x over sin x, the left side. Is it okay? So we have again showed right side equals to left side, and so the identity has been proven, right? Now here is another very interesting identity. We have to prove cosecant beta minus 1 times sine beta plus 1 is cos beta cot beta. Now in this, let us write the terms in sine. Cosecant is 1 over sine, reciprocal identity, right? So we'll begin with the left side, which is cosecant beta minus 1 times sine beta plus 1. Cosecant beta can be written as 1 over sine beta, we have minus 1 here, times sine beta plus 1. Now if I take 1 over sine beta common, then what do I get? I get 1 minus sine beta. Here I could write this as 1 plus sine beta, correct? Addition is commutative. So we get 1 over sine beta equals to 1 minus sine square beta, right? And what is 1 minus sine square beta? 1 minus sine square beta could be written as, let me write here, cos square beta. Well, we need cos beta times cot theta. So I could write this as cos beta times cos beta divided by sine beta, right? Divided by sine beta. Cos over sine is cotangent and this is cos beta. So I could write this as cos beta times cot beta, which is same as the right side. So we have shown how left side is equals to right side. Is it okay? So this was a good exercise to understand how to use a strategy to prove trigonometric identities, correct? So I have about 50 more questions to go. We'll divide them into part 1 to 10, maybe part 1 to 5. I'd like you to practice from those questions, apply these strategies which we have learned here, and see how easily you could prove trigonometric identities. I hope that helps. Feel free to write your comments and suggestions. If you like and subscribe my videos, that'd be great. Thank you and all the best.